All right, in this video, we're going to remind ourselves of the subring test, and we're going to specialize that to C. So just as a convention that I'm going to make right now, all rings have 1, because I'm not a psychopath. Okay, so all of our rings are going to have 1, and all of our maps, all homomorphisms, preserve 1. It's a basic thing that's that we're going to use over and over again in this class. All right, so what's the subring test? The subring test says, suppose R is a ring. Let's say S is a ring. And R is a subset of S. Then R is, let me say it differently. If 1 is in R, the multiplicative identity of S is in R. For all xy in R, x minus y is in R. That is x plus the additive inverse of y. And for all xy in R, let me put an implied symbol instead, make me feel better. X times y is in R. And then R is a subring of S. Proof of this is not so hard. Proof. Well, since 1 is in R, and since 1 in R, it has multiplicative identity, and R is closed under subtraction. I'm just going to say closed under minus. 1 minus 1, which is 0, is in R. So R has the additive identity as well. All of the remaining checks. Oh, sorry, one more thing. I guess there's another check here. For any x in R, 0 minus x, which is negative x, is in R. So it's closed under inverses, additive inverses as well. Okay, so it has 1, it has 0, it's closed under multiplication, it's closed under additive inverses. I guess we have to show it's closed under addition. Since it's closed under inverses, for any xy in R, we get that negative y is also in R. And so x minus negative y, which is x plus y, is also in R. So it's closed under addition too. And then to be a ring, what else do we need? Well, we need that the addition's associative, the addition is commutative, and we already checked that we already have 0 for the addition and we have additive inverses. These are inherited properties. Inherited properties. That is, they hold for every such thing in S, and so they're definitely going to hold in R because it's not about set membership. It's just, is the left-hand side equal to the right-hand side? Well, as long as one of the sides in R, they're both going to be in R, and so it will hold. All right, so, and then similarly, the associativity of multiplication is inherited. And the distributive property. If S is not, all of our rings are going to be commutative, but if it was not commutative, there's a left and right distributive property. But so I'm just going to say the properties are also inherited. That is, they hold in S, so they must also hold in R, because it's not about set membership. That's it. So this is a great test, the subring test. I've stated it a little bit differently than in the book. In the book, they say that you have to have 1, you have to be closed under addition and additive inverses as a third check, and then multiplication. But I've just combine the addition and additive inverses into subtraction, which is a common thing that you'll find in textbooks. Okay, so this is the subring test, which means whenever you're trying to show something's a subring, you use the subring test. Great. Now, there's a similar test, which is called the subfield test, which we might as well do while we're here. And it says if F is a field and K subset of F is a subset such that 1 is in K, for all xy in K, x minus y is in K, and for all xy in K, x times y inverse is in K, if y is not 0, then K is a subfield. Little k is a subfield of F. Let's just do this one real quick. Notice the third property for the subring test is instead of closed under multiplication, which in most rings you don't have the ability to divide, what this is saying is it's closed under division. X times y inverse is like x over y. Okay. All right, so let's just notice something. Since K is closed under division, for any non-zero y in K, it has non-zero elements because 1 is in K. 1 times y inverse is also in K because that's what it means to be closed under dividing by y. Thus, for any x y in K, we know that y inverse is in K. We get x times y inverse inverse, which is xy is in K. So K is closed under multiplication. Since it's closed under multiplication, subtraction, let's say since 1 is in K, K closed under minus and dot, K is a subring of F. We can use the subring test, and therefore we get all those checks. The only thing that remains to check is for it to be a subfield is we need to have multiplicative inverses of non-zero elements. Okay, we've already done that. That was done here. And we need to have a commutative multiplication. Those are the only differences between being a subring and being a subfield. But F is a field. Multiplication remains commutative in K. It can't be non-commutative because it's commutative for a bigger set. So K is a subfield. That is a subset that's also a field. And the field structure is inherited from F. All right, awesome. So this is the subfield test, which is again going to be slightly different than how it's stated in the book, and that's okay. In the book, it's that well, you have to be a subring, and you have to have multiplicative inverses. It's equivalent, of course. It's just stated slightly different. I prefer to think about the subfield test as this. So this first condition is a non-empty condition, and then closed under differences and closed under division. For subrings, you don't get division, so it's a non-empty condition, closed under differences, and then closed under multiplication. All right.